So in this lecture now, I want to discuss the efficiency of column chromatography and other separation techniques by describing this idea of resolution. So resolution, you can consider two peaks to be well resolved when they are narrow peaks, which means they have a small width at the base of the peak, and they have a fairly large difference in retention time, or delta TR. So resolution means that we have two compounds well separated from one another. The entire goal of this unit is to understand techniques that provide efficient separations of compounds, such as in chromatography. So well-separated compounds have high resolution, or chromatogram and separation technique is said to have high resolution if those two compounds come out and they have pretty different retention times and narrow peak widths. So recall that resolution, R sub S, is written as the difference in retention time over the average of the widths of the two peaks. So you can expand this equation and write it as the later retention time of peak 2 minus the earlier retention time of peak 1. So it's always a positive value over the width of peak 1 plus the width of peak 2, all divided by 2. So another way you'll see this represented is 2 times TR2 minus TR1 all over width 1 plus width 2. Now, time will be in units of minutes or seconds, and the width of the base is also in units of minutes or seconds. So resolution is a unitless value. So let me sketch two plots here to visually describe what it means to have high versus low resolution. Okay, so generally high resolution is classified as being greater than or equal to 1.5 or baseline resolution. So if you have two peaks that are quite narrow and well resolved, so this is compound 1 and this is compound 2. So the width at the base is width 1 here and width 2 given there. Delta TR is the maximum of the peak 2 minus peak 1. Okay, so those two compounds would say what we would say are well resolved. Low resolution would be something like this, where we have compound 1 eluting early and compound 2 eluting late. And the widths here have to be extrapolated because they do not hit the baseline. So now compound 1 comes out over a large range of times, and compound 2 comes out also over a large range of time. And the widths are overlapping here, which gives it low resolution. So now we can see that we have a pretty small delta TR between the maximums. And the bases of the peak are too wide. So the resolution is intimately related with the number of theoretical plates, N. So recall that capital N is the number of theoretical plates in a separation, and it describes the efficiency of the separation. If we increase the number of plates, then we increase the efficiency, or we get a better separation. And specifically, the resolution is proportional to the square root of the number of plates. So if n quadruples or goes from n to 4n, then the resolution, RS, doubles. It goes from RS to 2RS. So we'll see an equation in a bit that describes the exact relationship between the resolution and the number of plates. But making the separation more efficient or allowing for a greater number of plates is going to better separate these two peaks. So we would see that this diagram here would have a large number of theoretical plates, n, and the other peak would have a small number of theoretical plates. And it's always ideal to have a large number of theoretical plates. So the number of theoretical plates depends on two other values. So the length of the column, capital L, is an actual physical value. Okay, it's measured in units of meters, centimeters, etc. And this is an extrinsic value, or depends on, of course, the column and how long it is. The number of theoretical plates, as I mentioned, is unitless and describes the efficiency of the separation. And it also depends on how long the column is, or it's also extrinsic. Depends on the extent of the column length. The theoretical plate height is capital H. This is given in units of commonly micrometers, sometimes centimeters or meters, but this is an intrinsic value. So the equation that relates these is that the length of the column is equal to the number of plates multiplied by the plate height. So if n is unitless, then whatever the unit of the plate height is will be the unit of the length. And if you solve for n, then you can see that it's the length over the plate height. And therefore, increasing the length of the column will increase the number of plates. And that will increase the resolution, because we saw that resolution is proportional to the square root of the number of plates. So one way to get a better separation is to increase the column length. However, at the same time, you're going to pay the expense of waiting a longer time for your compounds to elute. So let's consider a column of fixed length L, because when you purchase a column, you don't have the option of modifying the length. So length L is given here on the x-axis. And I'm going to draw this column under two different scenarios, one that's efficient and one that's inefficient. So that length is a fixed physical extrinsic value. If we divide that column into n number of plates, where each of these red lines is one plate height, h, okay, then if I sum up all of the h values, right, I get n times h, the number of plates, times the plate height of each, gives the length of the column. Consider instead having a small plate height. Excuse me, having a large plate height, where there's a pretty large difference between each of these theoretical plates. So now the plate height is given here as h. So comparing these two columns, we have a small plate height on the left and a large plate height on the right. And we see here that the number of plates is inversely proportional to the plate height, which means we have a high number of plates for the column on the left, and we have a low number of plates for the column on the right. What we're going to find soon is that this is the efficient separation, when we have a very small plate height and a high number of plates, or we get a high resolution by having a small plate height. So we always want to minimize that plate height. The other separation here is very inefficient, or leads to a low number of plates and a low resolution. So plates and plate height are a little bit difficult to understand because you can't really visualize them. But let me remind you of a couple terms we've seen before, and then I'll more formally define the plate height. So a partitioning event, right? Remember the partition coefficient. This means that some solute X, which is in the mobile phase originally, equilibrates to the stationary phase, where it becomes bound to the column or to the packed stationary phase. And the partition coefficient, right, is the equilibrium constant for this process, where K part is equal to the concentration of X in the stationary phase over the concentration of X in the mobile phase. So what's ideal is having a large number of partitioning events. It's ideal to have maximum partitioning because it is the differential amount of time that X spends partitioning to the stationary phase as compared to a different solute, Y, that's going to cause them to spend different amounts of time in the column and thus come out at different times, right, on the chromatogram. So we always want a large number of partitioning events. We can separate two similar compounds with higher efficiency and higher resolution if there are many partitioning events. Even if it's just a small difference between two compounds in terms of their polarity or their boiling points, we can really take advantage of that if we have as many partitioning events as possible. And the plate height relates to this idea. So the plate height, H, is the distance, that's why it has units of length, along the column that a solute travels in between partitioning events. For example, going back to these columns above, if you have a solute, it will travel this far before it sticks to the wall or to the packed stationary phase again. And then it will travel this far and stick again and travel that far. Okay, so it's traveling a very small distance at a time and it's sticking very often. So I'll say that solute here is partitioning often. Whereas in the other column that was inefficient, now the solute travels a great distance along the column, a large portion of it, before it actually partitions or sticks to the stationary phase again. And then it travels another large difference or distance. So this has few partitioning events. So we always want, in an ideal separation, to minimize H, the plate height, so that the solute does not travel very far before it sticks to the stationary phase again. The more times it sticks to the stationary phase, the better separation we can get. So the way that you maximize the efficiency, the number of plates, is by minimizing the plate height. And that will maximize the resolution, since the resolution is proportional to the square root of n. So let me now apply those plots we had above. One had high resolution, where we had a large delta TR, and we had very narrow peaks. So this plot here has a, should say, a large number of plates and a high resolution. And it has a very small plate height. So that's the goal for every separation, high efficiency. Furthermore, if we had a chromatogram that looks like this, where you have compounds 1 and 2 that elute with a smaller retention time difference relative to their peak widths. Now, we're not too sure what's going on in here. This region is misunderstood and not well separated, okay? So now we have wide peaks. And that's resemblant of having a small number of plates, or a large plate height, where the solutes traveled a great distance before they actually partitioned again, and thus a low resolution. So in subsequent videos, we will talk about how we can maximize the number of plates by minimizing the plate height. But let me mention here that the plate height, and I should label this above as well so you can have it in your notes, right? The plate height is at intrinsic value, whereas the number of plates is extrinsic, and as is the length. So once the mobile phase is selected, the stationary phase is selected, and the linear flow rate, once all of those are set, then the plate height is constant. If you buy your column, your stationary phase is already in it. It is fixed. You can't change it. Once you select your solvent for your mobile phase or your carrier gas in gas chromatography, that's fixed. The only thing you can modify is the flow rate. And if you've set the flow rate at a constant value, then the plate height is not changing. Or this is an intrinsic value. So the intrinsic value H will not change if the length of the column changes. Okay. In other words, remember that L is equal to the number of plates multiplied by the plate height. So after the mobile phase, the stationary phase, and the flow rate are fixed, okay, increasing the number of plates is going to occur if the length is changed. But increasing the length or decreasing the length will not change the plate height. So once again, let me restate that. Once your mobile phase composition and your stationary phase composition are fixed, the plate height only depends on the mobile phase flow rate, which is, in terms of linear flow rate, written as mu sub x, or u sub x. So for example, right, if you have a column of length L, and we cut it in half so that it's 1/2 length, then what happens is the plate height, it's still the same distance in between theoretical plates. Plate height does not change. but the number of plates will go down by a factor of 2 to half of its original value. Conversely, if the length is doubled, somehow you magically connect two columns that are identical together and you double the length of your column. Still, the plate height does not change. It is intrinsic. And the number of plates will double. It is proportional to the length. So the goal in these separations, right, is always to maximize the number of plates and the resolution by minimizing that plate height, the intrinsic value. So for more practice with efficiency and column chromatography and understanding these terms of plate height, length, and resolution, along with theoretical plate number, you can visit Unit 2 of my analytical course guide at chemguides.com.